Hello, everyone. Welcome. This is the Ham House presentation. My name is Andrew Woodruff, Training Center Manager at Community Housing Partners Energy Solutions Research and Training. So I work at the Training Center in Christiansburg with a lot of great folks, a lot of great trainers. Sorry we couldn't be in person this year, but given the circumstances, I think we've got a pretty good product to offer for you guys. And yeah, I hope that it goes well. So to build on this a little bit, I'm going to have a little bit of other content that's going along with this. So I know you guys have all seen Grandma's house at this point. So we're going to use a little bit of that backstory to develop this, as well as just kind of the foundations of house as a system, of building science in general. So I wanted to make you guys aware of what we're going to do here. So without further ado, let's hop right in. So to explore the concept of house as a system, we really need to be mindful that there's a bunch of interactive, interdependent parts that are going to be affected by changes in the building. So one of the things that this tool is really great about is showing some of those complex connections between those different systems in the house that are maybe not so obvious. And this tool does that in a really obvious way that you guys should enjoy. So we're going to hop right in here. So the first thing to talk about, if we're talking about the house of heat, air, moisture, or the ham house, as you'll hear us refer to it as, is heat. So if you remember, we've got three different mechanisms for heat transfer in buildings. The first being conduction, the second being convection, the third being radiation. So we've got the ability to demonstrate that here. So I'm going to show you a little bit about the house, and then we're going to hop right in and explore some of these. So a little background about the house and what's going on here. We've got 3 stories in the house, 1, 2, 3. Starting on the first floor here, see we've got some burners back here. Don't worry, we've got fire extinguishers nearby if anything goes awry. But that's going to be our heat source. So we've got the lighting in the house as well as the candles underneath here are going to be the heat source that we're going to use for this example. So you guys can see the heat sources there. And then if we go up to the second floor here, be able to see our temperature. So we're at a balmy 145.6. So we've got a little X-Tech temperature and humidity meter in here. So we've got our temperature, then we've got our dew point, and then our relative humidity. So we're watching the temperature right now. And then nothing much up here, but we do have an an attic thermometer. That's got the attic temperature and relative humidity. We'll be looking at that here in a bit. And then last but not least, we have our ambient temperature thermometer kind of compare to. So coming back in here. So this is our ambient room temperature here right now. So we're at about 80 degrees, 26% relative humidity, and then 42.1 on the dew point. So if we're talking about temperature difference, which is the driving force for any sort of heat exchange, we've got 146 degrees inside the house. We've got 80 degrees outside the house. That's a pretty large temperature differential, almost 80 degrees there. So if my math serves me correctly. So if we've got that much of a temperature difference, which way do you think this heat is trying to move? Right? If we go back to kind of our basic building science, we know heat doesn't rise. Heat moves from hot to cold. Hot to cold, that's right. So if the inside of the house is 146.5 degrees, the outside of the house is about 80 degrees. Which direction is that heat going to move? It's going to move from inside to outside, right? So if we think about our 3 methods or 3 ways that heat can escape a building or enter a building, the first being conduction. What is true of conduction? Conduction is surface-to-surface contact, so we have to have physical surface-to-surface contact. And in terms of building products, our insulation, our framing materials, those are the kind of things that are going to prevent that heat from escaping in the wintertime or prevent the heat from coming in the summertime. So it's the building materials that are going to protect the building from conduction. So insulation is your protection from conduction. So in our house here, we've got a few different little insulated areas. And what I'm going to do is I'm actually going to show those to you with a thermal cam. So with this thermal camera, we got here, nice little unit here, the FLIR one that attaches to your iPhone. I'm going to fire that up, and we're going to go right into the app here to show you guys what's going on. So I'm going to step over here. So now you're seeing a thermal image of the ham house. So the ham house, the way that it's constructed here, if we go back, let's leave that alone here. The way that it's constructed is plexiglass on the front, but all the walls are insulated. And then you can see we've got an attic up here. Attic has insulation across most of it except for the attic access. So I'm going to give you guys a little preview what's going on in the attic. So I'm going to crack the lid here. It doesn't do very well with reflective surfaces. So if you guys can see, here's my attic hatch. And if I pan across here, I can see some cool insulation. I can also see the hot spots that I've got for my framing members in the attic. So my ceiling joists are showing up as hot spots because it's hotter in the house than it is in the attic. So there you can see that insulation is doing its job in the places it actually is in contact with the air barrier. So if I pan back over here, I may have an air barrier in the terms of an attic access, but I don't have any conductive heat loss protection there. So I'm seeing all that heat moving into the attic. So that's a really good image of conductive heat loss. So I'm losing that heat from the house. And then if I pan over here to the side on my house, I can see my wall assemblies here. And each of these wall assemblies have 3 cavities. And you guys can probably see one of those cavities looks a little bit different than the others. And I've got another wall section a little bit further down here. This is a window. A window with some insulation in there. That one's clear. But my other framed wall, see something else is going on here. So that surface temperature, that hot surface temperature there, that's going to show me a lack of something in this wall. Any guesses as to what that might be? Insulation. Yeah, so my insulation is missing from one of these cavities. So if I take my wall section out, flip it around, I can actually see that I've got, just like we saw, there's an empty wall cavity. There's some spray foam in one wall cavity, some unfaced fiberglass batt in another wall cavity. And this wall is made out of wood. Okay, so it looks like our framing is giving us a little bit of R value, a little bit of conductive heat loss protection. So I'm going to put this one back and pull out the other wall section. I saw up top, another thermal shot here. This one seems like it's a bit hotter, kind of all the way around. And the reason for that, pop this off. Take a look here in the frame. We're actually, devoid of insulation here. This is metal frame. So that metal, as compared to wood, is going to conduct heat more readily. So it's not showing up like it's as much protection because it's not. And then we do have the one side insulated over here that's actually insulated quite poorly. Spray foam is not in proper contact. So this wall compared to this wall, put these back up here. This one's got a lot more heat loss as compared to this one down here. So you can actually see that in the surface temperatures as well. So that is conduction. So we've shown you the heat moving out of the building due to that temperature difference, that 150 degrees inside, 80 degrees outside. That's a massive temperature difference, 70 degrees. That's going to be a huge driving force for us here. So that heat that's building up inside the house wants to readily escape to the outside of the house. So that's conduction, first mechanism of heat transfer. Does anybody remember the second one? Credence, Clearwater Revival, conduction, convection, and radiation. So in order to display convection, we've added stories here. So we've got a 3-story house. We've got some stack effect going on. And we know that if we've got a temperature difference between inside and out, that heated air is going to have the tendency to move in the building. So that heated air wants to rise up and out of any holes that are in the top of the building. And then as we have CFM that escape, what has to happen? We have to have CFM coming back in. You have to have that air coming back in from somewhere. And usually that's going to happen lower in the building. So we're going to explore a little bit about this and look at the neutral pressure plane location depending on the leakage location we've got inside of the house. So what we're looking at here, you can see the ham has a crawl space down below. You see that? You've got your crawl space. We've got an attic up above. And then I'm going to turn this to the side a little bit so you can see that each of these spaces have venting. So this crawl space door slides open and closed, so we've got venting here. And then we've also got attic venting high in the building here that we're actually going to have that connection to the outdoors. So we do have some sort of opening high and low. This is in the exterior kind of portion of the building. And then on the inside of the building, I've got little slides that I can actually change the connectivity to those spaces. So I can open a hole down here inside of the crawl space. I can open a hole here between the house and the attic. So what that's going to do for me is going to give me those pathways, so I can kind of explore what's going on. And there's a couple different ways to do this. The first one's just a visual exploration. So what I can do is I can turn on my smoke. Got some smoke here. In my crawl space. If I hit the right switch. There we go. I'm going to kind of close everything off. And as we mentioned earlier, that heated air has the tendency to rise. It's more buoyant, it wants to move, and it's going to be driven or dictated by the pressure inside of the house and the temperature difference between inside and outside. So I'm going to measure the pressure in just a bit and show you the differences. But I've got some smoke kind of roiling out here. So if I were to open up a pathway from the crawl space, close this attic pathway, make sure that's closed. You can see the smoke. I've completely opened the crawl space. So you can see the smoke just boiling into the crawl space there. But where is it going? Not really going anywhere. It's kind of shooting up and out into that space and then just kind of hanging out. So that's because I've opened that pathway. There's no pressure, there's no force that's going to allow it. There's no push that's going to allow it to go out of the attic access. So what I'm going to look at now is what happens to that smoke if I create an opening inside of my attic here. I'm going to open this attic access. Immediately, what's happening with the smoke? Smoke is now rising up, and it's actually rising up through the structure all the way into the attic. I can see it around this light now, the smoke. And then if I come over here, I've got a little flashlight. See you guys, little flashlight and a little background material so we can see what's going on. So we may not even need this additional smoker. you guys might be able to see what's going on. So the air in the attic is being forcefully expelled now. So it's moving up through the building, which is a big part of it, is how tall is your building. That's going to be a driver for stack effect. It's the distance between the height from your neutral pressure plane, and the taller the building you have, the more powerful that stack effect is going to be. So with our little 3-story building here, we've got a lot of stack effect going on. And as I mentioned, that air has the tendency to rise up and out of the structure. So now, if I turn this over to the side just a bit, you can see the same relationship just in reverse down here at the bottom. Now that air is being drawn in from the outside in the crawl space and going where? Going right into the house. So if you think about that from an indoor air quality perspective, it's not a good thing. Definitely not a good thing. Let me kill my smoke here. So if we've got that airflow, we've got leakage in the top of the building, we've got leakage in the bottom of the building, and that air is flowing from the outside into these other regions, and then moving on into our house. Simply what that means is that we're going to be breathing in this condition when it's warmer inside the house than it is outside the house. We're going to be breathing whatever air that's bringing in. That is convection. We are losing heat because that tendency for that heated air to rise up and out, and then it's drawing in whatever makeup air it can. And we're not, I mean, I know you guys have been in crawl spaces. This is not a great place to be. I don't like to be there unless it's a enclosed crawl space and they've got the nice liner and everything is bright and pretty. But typically, this is the nether regions of the house, and I don't want to be breathing my air from there. So that's a good visual just to kind of show you the way the stack effect works. Now what we're going to do is we're going to explore a little bit via the manometer. We're going to actually measure the pressures inside of the house. So I'm going to switch over here. I've got a couple of pressure probes just hooked up to DG1000 and a couple of manometer hoses here. So I'm going to place one of these at the top of the building, and then I'm going to place the other down at the bottom of the building. Okay. What that's going to tell me is the pressure on channel A, the red hose, is going to be the pressure at the top of the building. The hose down here is going to tell me the pressure at the bottom of the building. Got my manometer here. I'm measuring pressure inside the house at those locations. So channel A is hooked up to the top, channel B is hooked up to the bottom. So I'm going to focus on channel A. I'm just going to kind of move down the house. So up here at the top, I've got a positive 0.4. Move down. Next pressure, positive 0.3. Move down again. Positive 0.2. So as I'm moving away from that location, that leakage location, I'm moving towards what's called my neutral pressure plane. So eventually I'm going to hit a pressure that's equal to that of the outside. So again, the greater the distance from that neutral pressure plane, the more pronounced the pressure is going to be. So let's keep dropping down here. Okay, I think I'm near the neutral pressure plane. I just hit 0 on channel A. I'm going to draw a line here. That's going to represent my neutral pressure plane. And what we're going to see happen, once I drop below my neutral pressure plane, that's kind of like 0 on my number line. So once I drop below the neutral pressure plane, I should see the numbers become negative. So let's see here. Negative 0.1. Let's drop down again. Negative 0.2. And then you can see on channel B, I've got a probe already at the bottom of the house, and I'm at a negative 0.4. So I've got a pretty even amount of pressure, high and low, but really all that that's telling me is that the size of my hole from the attic, or from the house to the attic, and then from the crawl space to the house is the same size. It's really all that that's going to tell me. So I'm going to plug this back in, and what I'm going to do is I'm going to manipulate my hole sizes, top and bottom, and we're going to see what happens as a result. So the first one I want to do is I'm going to seal up the attic. If I seal up the attic bypasses, what's happening to my pressure? So if I look on my channel A, my pressure at the top of the building, 0.8, 0.9, and then down there at the bottom, it's 0. So really all that's showing me is that the range of pressure is the same, and the range of pressure is really just dictated by the height of the building, and then the temperature difference between inside and outside. If I didn't have any temperature difference between inside and outside, I wouldn't have any buildup of pressure. If my house was 1 story instead of 3 stories, that's going to be a different reading in terms of the pressure, because there's not as much distance between the boundary, the pressure boundary, and the neutral pressure plane. So I'm seeing I've basically, by air sealing at the top of the building, what I've done is created a shift in my neutral pressure plane. So my neutral pressure plane actually dropped down to the very, very bottom of the building. So now everywhere along this wall is going to be a positive pressure, slightly positive relative to the outside. And ideally, in terms of indoor air quality and kind of control, that's what I want to have. Is I want to have a building that's sealed at the top, well, top and bottom, but especially first at the top, to create this effect in controlling that stack effect and moving that neutral pressure plane down. Now, what if you did the reverse? Let's say that for whatever reason you decided to seal up the penetrations and bypasses in the crawl space, but you decided you couldn't access the attic for whatever reason. Crack my attic back here, and I seal up my crawl space. See a complete and total reversal. So I went from a positive 0.9 on channel A, that's the probe at the top of the building, to a 0, and then now my neutral pressure plane is completely shifted. It's completely flipped locations. So now my neutral pressure plane is up here at the top, and then anything below that neutral pressure plane is going to be a negative pressure. So the whole building in this scenario is negative. And the further you get away from that neutral pressure plane, again, the more marked those pressures are going to be. So down here at the bottom, I'm seeing a negative 0.1 and negative 0.9. That's a huge increase in pressure. So that's going to pull more of those contaminants into the house in this scenario. So again, just to recap, convection is the heat transfer mechanism dealing with airflow and air leakage. Because that heated air has the tendency to rise up and out of the structure, I have to control that by sealing up bypasses in my ceiling and floor. So if I have equal bypasses between high and low in the building, then my neutral pressure plane is going to be about smack dab in the middle, and I'll have a field of positive pressure and a field of negative pressure. If I seal the attic bypasses, I'll drive that neutral pressure plane completely down, and then I have, if I've limited the amount of air that's going out of the building, I'm also limiting the amount of air that's coming back into the building. And the reverse is true if you were to only do the crawl space. But we know in most applications, we're going to seal both locations, seal all the penetrations, whether it's in the attic or the crawl space. We want to seal them all. But if we had to pick one to start, this kind of shows you where you want to start. I want to start at the top of the building because that's going to have a great effect on that neutral pressure plane. And 2, typically when you're talking about stack effect is greater in the wintertime. You have a greater delta T in the wintertime. So if I want to cease this activity, this heat flow, I want to seal this location first. because if I stop the air from going out in the first place, I'm certainly going to stop the air from coming back in. Okay, so we've discussed our heat flow mechanics of conduction and convection. Lastly, radiation. Really not too much to get into in terms of the ham here, but radiation is simply a difference in temperature between two surfaces within line of sight. So the sun is about the only thing that you would really be able to relate to here, is because, I'm going to get radiant temperature, say, as the sun heats up the roof deck, that roof deck is going to change temperature. It's going to be hotter, and then that heat is going to radiate down into the attic. You could say I've got radiant heat energy from my flames down here in the crawl space, my heaters. So that flame, I'm actually getting radiant heat energy. It's going to be warming up all the surfaces around those little heaters. Air, and really the only thing that we didn't talk about in terms of airflow is for air to move in the first place, you have to have a couple of things. And those conditions, those things are, I have to have some sort of pressure difference, and I have to have some sort of hole. Got to have a pathway in a pressure boundary in order to have that. So you guys saw the air movement via stack effect, via that convective loss, but just want to make sure that that was clear. You have to have some sort of pathway to that space or through that space, and the pressure difference across that pressure boundary to actually have any sort of airflow through that opening. So I'm going to clean up a little bit here, erase some of my artwork, and then we're going to move on to moisture. Final chapter now. We've talked about heat, we've talked about air, now we're ready for moisture. So a couple things that we're going to be looking at here specifically. We've got our situation kind of unfolding here, and we like to do the grandma's house routine. We seal up the house. Now she can't see when Red's coming to visit. We get condensation on the walls. So they warm up the walls with some insulation and put it in a bath fan just in case. And then, oh no, the stove is back drafting. So we're going to try and replicate that sequence of events here. So where I'm going to start out here is by kind of just laying out my ground rules, what we've got going on. So I've got 10% relative humidity, nearing 160 degrees, and my dew point is 76.3. And if you guys remember what dew point is the temperature at which condensation will occur. So if I have a surface that is at or below that dew point, then condensation is going to show up on that surface. So if I incorporate a little help here, got my spot infrared thermometer. I want to keep that nice and close to the building. And then I've got some clear plexiglass here, and that's really not going to be too great to get measurements for, because it's going to say, I've got 120 degree surface temperature here, which is not quite accurate. So we've got some really high dollar, really expensive stuff. What is this called again? Vinyl electrical tape. Yeah, so really high dollar stuff here. Attached on the plexiglass, so I'm going to be able to take surface measurements and kind of see where we're at. So we'll set the stage here. So again, my dew point is 76.6. I don't see any condensation occurring here. I got nothing going on. Maybe there's a reason for that. So I'm going to shoot here about an inch away. So my dew point, 76.6. My surface temperature here, I'm at 102. 102 even down here. So because I'm not below dew point, I have no condensation. I've got no chance for condensation to occur. I'm only at 10% relative humidity. It's really, really warm inside the house. I'm not there. So I have to get either this surface to drop in temperature, or I'm going to have to add humidity here. So 10% is really dry. That's not something that you're typically going to see in a house. So what we're going to do, we're going to kind of explore some other surface temperatures here and just see what's going on. We're going to add some moisture to the equation. We're going to see what happens. So again, I was at 102 down here, 101, about 97. This little insulation behind an air barrier here. So I've got that on the second floor here. And then we've got some insulation just kind of laid up against the plexiglass, really just trying to show the lack of a proper air barrier on the back side. So you can see here, that's going to be a little bit warmer than this because it's got a proper air barrier, plexiglass on one side and tape on the other. And then I've got a couple more that I'm going to shoot for you on the side. Kind of to drop this thing on my head. So down here, and you can kind of see it in here, there's some insulation sitting in this wall cavity. And what we wanted to show was the difference between an uninsulated surface and an insulated surface in terms of a vapor barrier. So this plexiglass is going to act as an outside vapor barrier. So when we start to add moisture to the equation here, that moisture is going to want to move from inside to out because out here, we're not seeing it yet. We're only at 10% relative humidity, about 25% relative humidity in the house, or excuse me, out of the house, and 10% relative humidity inside. So we've got some insulation down here. That surface temperature is at 88 degrees, holding steady. And then let's just get this thing out of the way here. So 88 degrees, holding steady. This upper one here, 105 degrees. So you can see that insulation is doing its job, and it's going to keep kind of the lower half of this a lot cooler than the upper half because it doesn't have any insulation. Okay. So now I think I'm ready. Just like in Grandma's house, she wanted to add that pot of water on the boil just to keep the humidity level up. So what I'm going to do is add some water. We're going to watch what happens. We're going to see how this changes the game here. So I've got a cup of water, got a little syringe. I'm going to move over here, take off my door. I'm going to add some moisture to the equation. See how that changes things. Do 2 squirts apiece. Okay. So now we've added some moisture to the equation. So I've got this probe. This probe is actually going to be going down into this kind of basement level. So I'm expecting that as that water starts to vaporize, it starts to boil in those little butter dishes, that I'm going to see an increase in my relative humidity. When I see an increase in my relative humidity, I'm also going to see an increase in my dew point. And that's where things are going to get interesting. So I've added all this water to the equation. Let's see what happens. So still holding steady at 10%. Temperature dropped down a little bit, had the door open. So it goes. But we're going to see that relative humidity start to spike. And then the dew point is going to spike right along with it. So quick temperature check. 98 degrees. About 100 degrees. 98.5 degrees. 92. And 104. So still waiting for my gauge to catch up with us here. So I can see the bubbles. There's definitely some water going on. So if we're talking about dew point rising and we're talking about what we're expecting to see here, the coolest surfaces that I've got, kind of got some over here with this wall, the insulated wall, but usually the lower the point in the building, that's where the cooler air is going to sit, and that's going to be my lowest surface temperature. So I'm going to expect as this starts to develop here, I'm going to see this moisture just jump to 13% relative humidity. The dew point jumped up pretty quickly on top of that. 15, 16. Okay, so now we're starting to see a little activity. So we went from 10% to 17%. Dew point now is all the way up to 86.4. So not quite there yet, but I anticipate that this is going to get going pretty quick here. So then my gauge hasn't quite caught up to what's going on here. I don't know if you guys can see that down at the bottom. Starting to see, what is that? Getting a little froggy in the basement there. So starting to see that condensation, and as we kind of theorized, that's going to start happening from the kind of the lowest point in the building, and then it's going to start spreading because again, that should be the lowest surface temperature that you've got in the building. So we're going to keep an eye on this as it's developing here. 21% now. Dew point 92.8. We're getting in the zone. This is going to be really close. So I can start seeing the moisture is filling in on the edges here, starting to run across the bottom. Going to get really foggy really quick here. So again, let's just do a quick check here. Surface temperature down here at the bottom is about 93 degrees. We just surpassed the dew point of 94 degrees. So remember, anything at or below the dew point is going to have condensation present on that surface. There we go. Really starting to see it fill in here. Dew point's not hopping and skipping like we would expect, but getting there. Starting to fog up. You guys can see that. Fogging up here. Quick check on the sides of the building. Maybe expect a little quicker condensation over here as well, because we've got, because of that insulated pocket and kind of the distance away from the heat source, this actually ended up being a location with the lowest surface temperatures in the whole building. So, take a look. Ooh, yeah. Let's find the angle that works good for that. You guys can see that condensation on there. So you might be wondering, well, how is that possible? How do you have condensation occurring on that surface? You've got fiberglass there, right? That fiberglass should be doing something, right? Well, if you guys have ever really thought about it, fiberglass in this application is more like filter glass. It's not going to stop airflow. So what we have now is this air pressure, this vapor pressure, this want of this moisture to escape via the path of least resistance if it can. But it's moving through this fiberglass insulation, and then it's touching a vapor barrier. So it's condensing on that outside surface. It can't go any farther. So under this condition, this house is just going to keep pumping moisture, pumping moisture, pumping moisture. It's going to keep moving through that fiberglass, and it's going to condense on that surface. So it's not happening up above it. You can see that. So up here in the top half, that's not happening. It's only happening down here. Yeah, see that? Really getting some condensation now. So because we don't have a proper air barrier, and because we do have a vapor barrier on the exterior there, we've moved through, hit a condensing surface, and now we're just going to trap that moisture in that wall. So let's start moving around here. Okay. We're getting there. So now we can see droplets starting to form in the bottom. Starting to work its way up and around. Starting to see some developing on the edge here. You can see that a little bit. And really this whole bottom floor, it's a kind of a different, you can see a film, a cling of moisture kind of starting to develop here. Is that helping? Oh, that's the veneer on the back. That looked really cool there for a second. Starting to show up. starting to move. Very cool. Okay. 29%, dew point's 103. We've already got on the second floor now, moisture starting to show up. It's going to obstruct our stuff. One thing I did have, just closed it. Keep tracking up here. Nothing on the first floor, but I did trying to get a little air movement. Let me see going on up here. Okay. Grandma thought she had a roof leak. What do we see going on? So this surface temperature is going to be pretty cool. Let's check it out. It's 89 degrees. Over here it's like 97 degrees, maybe a little warmer. So you're seeing as that heat was escaping, it was starting to warm the roof deck in this one location. Actually warmed it past the dew point. And then now everywhere else that was below the dew point is now condensing. So this is where you might think, well, yeah, I've got a roof leak. No, this is that warm, moist air rising into the attic, condensing on that roof deck surface and then dripping back down. So if you've ever had the roofing contractor try and sell you on a power vented attic fan to fix your moisture problem in your attic, your moisture problem is probably happening in the wintertime. And that's not even going to touch it. Only has the potential to steal your air-conditioned air out of your house and use electricity. So not going to be very beneficial. Okay, so now we're in business. This is looking good. So you guys can see we've got a tremendous amount of moisture starting to form. It's condensing, it's beating up. And we've got some interesting stuff going on here with the insulation. So we wanted to manipulate the surface temperatures in this building a little bit. We've got 2 locations for insulation. So this one, I don't know if you guys can tell this. This is on the outside. I can touch it, I can move it. This is exterior insulation. So if you think about what that exterior insulation is going to do, the heat's trying to move in which direction? From inside to outside. So this insulation is going to keep that surface warmer or cooler? Keep it warmer, right? So if I draw a little outline here around where this was, I'll take this down, check that out. No condensation whatsoever on that surface. Why? Why is that? Well, again, because my dew point temperature, that insulation kept that surface above the dew point. Therefore, I didn't have any condensation present on that surface. Okay? So moving on up here, this insulation is trying to keep this surface cool. It's on the inside, can't get to this one. Inside here, 102 degrees. And we're seeing the same thing we saw on the side over here. We're seeing that condensation forming all around there. So that's, again, showing you that without a proper air barrier system around this fiberglass, that air is going to move through, and then if it hits a condensing surface, it's going to condense. So if we look over here, we have something that's even lower. It's 99 degrees. And by the way, our dew point is 109 degrees. So 99 degrees there. But there's no condensation. Nothing. Why is that? That's because we've got a proper air barrier that's going to prevent that moisture-laden air from trying to get through this wall to hit this cold surface, because that's where the air wants to go. It's hot and it's moist. It wants to go to that cold surface, but it can't because we've got an air barrier. We controlled that air movement. Okay. Now we've even got fog occurring up top. Man. So, we might do this. We might have caused this issue by air sealing. So we go into the building, we seal it high and low. We did what we were supposed to do to control convection like we talked about, but we didn't pay attention to the house as a system. So we're seeing now the ramifications of what we've done. So we've got this issue. We've got this moisture. How are we going to deal with a moisture issue inside of the house? We're going to provide some ventilation, right? But just like in Grandma's house, they added the exhaust fan. That's what we want to do. So let's check this out. So I've got my little fan here. It's going to be pretty cool. I'm going to put a fan on the building. Take off a window over here on the side. Close this up. This is going to be an exhaust fan configuration. Got some sweet little lights on here. Check that out. That's the business. So if I put my hand up here, it feels like, it's like somebody's breathing out here. I've got my mirror. Handy dandy little mirror here. What's going on here? See that fan is getting a little bit foggy? Yeah, it's because that moisture is being exhausted out of the house. This is, like I said, it feels like somebody's hot breath on my hand here. But immediately, what have we seen happen? Ta-da! Everywhere we look, moisture is being resolved. Moisture is being exhausted out of the house. We can watch this move down the wall. It's being removed from all these areas. That top floor that was starting to condense, no longer. So we're exhausting this moisture out. That's awesome. But one of the concerns that we have is when we kind of focus in on an issue like this, well, how we've tightened the house up. Now we've got this moisture problem. We can see it. It's a visible complaint. We need to deal with it. How are we going to deal with it? We're going to provide this ventilation. Well, what are some of the unintended consequences of ventilation? So we've got a negative pressure in the house. I know that because I've got a fan here. Could measure my pressure inside the house with my manometer. Get that turned back on. So I'm exhausting the air out. I see the relative humidity is dropping and the dew point along with it. So this is a good thing in terms of moving that moisture to a place where it's not going to be an issue anymore. But one of the unintended consequences, you guys know the drill here. So let's go ahead and unplug my exhaust fan. Turn that off. Got a little fireplace here in Grandma's house. Fireplace. So take my damper off. Need that. So this is Grandma's house, sealed up. I've got the crawl space door closed. I've got the attic, everything's sealed up there. My exhaust fan is turned off right now, it's unplugged. And lo and behold, what do you see? So this fireplace, when it's running, is actually drafting properly. The smoke is going up and out in its intended direction, as we would expect. So what we want to see is what happens when we've got an exhaust fan that's going to play with that. So I'm going to turn my exhaust fan on here on the lowest setting. Ooh. And immediately, what happened? Let's do an instant replay here. So I've just opened up some combustion air to the back of the fireplace. We see that the thing is drafting properly. Everything is working as intended. But with the exhaust fan, if I seal that combustion air up, it starts to slow. Dramatic backdrafting inside the house. So less than ideal. So my exploration of this ventilation conundrum is, well, we've only got two options here, right? So we either provide dedicated makeup air to the appliance, and that maybe could be done through, if that's a furnace, it's a 90+ furnace, air originating from outside, or we make the house leaky again. So if I seal this up, make the house leaky again. Maybe that'll work. Kinda close there. Obviously, if you open the front door, that's going to provide you some air. But that's an issue for us, right? We're not hitting the marks that we need to hit. I'm trying to seal up for a reason. I'm trying to make this intentional. I need to seal up these openings for indoor air quality. I need to seal them up for house's system. But what good is indoor air quality if I backdraft my furnace, right? Backdraft my water heater, cause these issues. So let's take a look here. Look up my pressure gauge throughout the building. We'll do a pressure gauge top and bottom. How about that? Pressure gauge. So here I'm seeing, see that? Negative pressure throughout the building, top and bottom, because I've got my exhaust fan here. So if I provide some sort of makeup air, see the pressure, it's irrelevant, right? Goes away. It's because it's getting its air from the outside. So this exhaust fan and the fireplace are now competing for this air. So what I want to do here, if I crank it up even farther, I can really increase the negative pressure. This is going to be just outrageous here. So why exhaust? That's maybe the first question. So again, one of two options. I provide makeup air directly to the appliance and everything works. Even if I were to crank up the pressure on the fan, everything's still going to work as intended here. If not, well, why ventilation? Why exhaust ventilation? We know we need ventilation originating from outside, but why exhaust? You may say ASHRAE. ASHRAE doesn't specify which type of ventilation strategy is required. It simply states if you replace things or change things out, what those requirements are for those systems, but it doesn't tell you negative, positive, or balanced. So if I take my fan, turn that around, and we see what happens to the pressures. Positive. Positive throughout. What's happening with my smoke? So now I can see that my building pressures are going positive. My smoke is kind of kicking on here. I may have actually turbocharged my wood stove here. It's kind of kicking, screaming. You guys see how fast that's moving up and out of the house. But I've positively pressurized the building, so I'm no longer backdrafting. I might be burning more wood, using a little bit more fuel, but I'm not actually backdrafting anymore. So I can turn it around and I can do supply pressure, positively pressurize the building envelope. Or best case scenario, maybe I have two fans, or maybe I have an ERV, or maybe I have an HRV, some sort of balanced recovery. So I'm going to add another fan, exhaust fan to complement my other one here. So let's turn this on. Now I've got one fan exhausting, one fan blowing air in. I can tune this right up here. Make the pressure almost neutral in the building. You guys see that? Essentially, it's like there's no pressure being exerted on the building whatsoever. So show you guys what that looks like on the side here. This would be a pretty classic no recovery setup. So this fan is blowing air into the building. This fan is exhausting air out of the building. So it's a balanced pressure. So regardless of what type of ventilation you choose, there's pros and cons for each. But the goal is that we can do the air sealing in the building that we want, and then through ventilation, whichever ventilation strategy that we do, that's going to ensure that we've got healthy indoor air for those occupants to breathe. But it's not healthy if it's coming down the food pipe. Makes sense to me. So that's about it for the House of Heat, Air, and Moisture. I want to thank you for joining us today. Thank you for participating in the conference. We really appreciate it. We hope that you'll give us your feedback and let us know how we did, and if there's anything else that you'd like to see covered or anything that you'd like to be covered in a different way. But thanks again for your time. Hope you guys have a great day. We'll see you next time. Thanks.